Hello and welcome to Das Nostalgia Podcast, episode 17. As usual, I'm your host Anatoly, and today I have another wonderful guest with me for your listening pleasure. Sir, please introduce yourself.
Hello, I'm John Connolly. I'm a remote DOS programmer.
Excellent. Well, we are here today to talk about programming for DOS in general, but before we get to that, do you, sir, have a story about your first experience with an IBM PC or compatible?
I certainly do.
Alrighty.
Now, my first experience with computers was roughly just after the DOS era, so I was more versed in Windows XP. So my first experience with DOS, well, I found my dad's old collection of discs, old collection of all these old DOS games he'd bought all over the years. And I found this boot disk in it saying MS-DOS, and I was like, what the heck is this? So I put it on my disk drive on my very old computer, and nothing happened since I was in Windows, and I was like, that's a bummer. And so, at the end of the night, turned my computer off, and then when I came back to turn it back on the next day, checked the floppy disk drive, found something in it, and booted into DOS, and I was like, what the hell is this? Am I in the Matrix or something? But no, I wasn't. I was in DOS, so I was a bit confused about it being a keyboard interface, but I quickly learned it, and I figured out how to go into freeware games in DOS, and it was honestly the greatest experience of it ever.
Nice. And how did that branch into sort of programming?
Well, at one point, I was just like, I really want to make games for PCs, and I was making games for Windows already with this crappy little thing called Game Maker.
Mm-hmm.
But I wanted to branch into like assembly, so I could have more control over the computer. And as a result, I started to learn to write for other platforms like the ZX Spectrum and eventually IBM PC.
Wow, neat. All right, well, that's actually pretty impressive. Alrighty, sir, so shall we begin?
Okay.
Alright, well, take it away.
So, the IBM PC, it has got a lot of good sides, a lot of advantages, and a lot of downright flaws. And one of them is the segmented memory in it. Now, if you're running in real mode for your application, which is most likely the case, well, your memory was segmented into little 64K blocks. And you would think, oh, well, since it's a 20-bit address because we've got 1 megabyte to work with, the 16 bits must control the 64K, and then the 4 upper bits control the segment. No, that's not how it works. It's actually very, very confusing. Basically what happens is, it's got about, I think it was 16-bit segment register, and then a 16-bit offset. And they shift the offset along by 4 bits, and then they add it to the segment register. And this is very confusing.
Right.
Obviously, because you're just like, what the hell is this? How the hell does this work? But most of the time, you're not going to need to worry about that if you're like me and you're doing very small programs like little games. So,
right.
The segmented memory, that was completely abolished in protected mode. Protected mode, you were like, oh my god, I can access 16 megabytes of memory and 1 gigabyte. This was in the 80s. 1 gigabyte of virtual memory.
Uh-huh.
You think this is amazing. You're like, wow. And then you read further into it, and you can make your programs for protected mode, but only if they don't use self-modifying code, only if they don't use segment arithmetic, and you can't use direct hardware access in protected mode, and you can't use BIOS calls in protected mode because the BIOS interrupts have been reserved by Intel.
Right.
So the only way to access hardware now is by, well, you can't. Because, look, direct hardware access, well, that's the fastest way to access the hardware, that's locked out. So you would think, I'll just use the BIOS function then. BIOS functions are locked out. So I haven't figured out a way to get any programs to run in protected mode yet, because it is just an absolute nightmare to work with. The other bad thing about it is that you cannot execute data. Now you might think, when am I ever going to have to execute data? Well, I'll give you an example. There was a recent demo by Jim Leonard. I think you talked to him in an earlier episode. Jim Leonard is called 8088 Domination. Where his video codec, since the IBM PC 5150 was too slow to handle branching, well, he just made like a video compiler where it was actually outputting code, not video. So you can't really do that in protected mode because you're executing data. So there's that downside. And they realized their faults with protected mode. So they introduced virtual 8086 mode so that you can actually do direct hardware access in a virtual 8086 machine. This took 1 megabyte of RAM, which is basically all the RAM you had in all of those old PCs, so you were completely screwed then. And basically, there was no... I haven't found any real way to run programs in protected mode. And I know there's a lot of game developers that have, but honestly, I just can't see how you can do it without direct hardware access. It's mad. On the bright side, you've got 16 megabytes of RAM. So, how's that for an opposite?
Yeah, well...
What use is it if you can't even access the friggin' display? Or if you can't even read the keyboard? As soon as you go into that, your computer just becomes a black box sitting on the desk. So, protected mode, you can access 16 megabyte of RAM, but you can't do anything with it because you can't access hardware. So what you have to do is, if you want to fit all that data in real mode, you have to use compression techniques. Now, compression techniques, I've only used simple ones, nothing like LZW, whatever it is, because those have patents on them. But there are a few compression techniques you can use in your programs to compress graphics, compress sound, whatever it is you want to compress. So, if you're using cartoonish graphics for your games, like graphics like the ones found in Leisure Suit Larry 7 with the main character, well, you can use run length encoding because it's mostly solid colors. So, run length encoding will be a real good compression technique there. Basically, run length encoding. Instead of encoding the pixels individually, you say what color the pixel is, and then you say how many times to repeat that value. So if I had 256 color ones, I'm just working in VGA mode, yeah? If you had 256 color ones in uncompressed data, you would encode that as 256 bytes, which all contain the value 1. In run length encoding, you would encode that as the value 1, and then in another byte, 256, which means repeat this value 256 times. Like, Sierra games used a lot of those compression techniques because they had loads of pictures, loads of graphics, and loads of sound. Like, specifically, I remember when I was looking at the Sierra Creative Interpreter 0 engine, and they actually use run length encoding for the views with the little character images. So they do that for the character images, and I think everything else is encoded in this. I can't remember the name of the compression algorithm. All I can remember is that it's patented by some greedy bastard company.
Thing about Sierra, right? Sierra also somehow managed to save up on backgrounds in AGI and SCI0 by having them in this really weird vector format.
Yeah. Graphics compression, if you've got full screen, if you've got full screen graphics, you can sometimes do vector compression. Now, this means the backgrounds you've just previously drawn, you have to redraw them in the vector format so that they're compatible to the vector format, because you can't just convert a bitmap to vector. That'd be crazy. But the vector format, it's very good at compressing the backgrounds. Like, as you said earlier, like Sierra used to do that with their backgrounds in the AGI and SCI engines all the way up to, I think it was SCI 1 when they stopped doing that with their hand-painting backgrounds now. But the vector backgrounds, the upside is that it saves on storage space. The downside is that
You have to draw them.
you have to draw them. And if you're not using a fast algorithm like Brenson's line algorithm, I think that's his name, Brenson's line algorithm, well, that means your computer's probably going to be locked up longer than if you just loaded the background from the disk in bitmap format.
Yeah, it was quite something. Like when I actually finally saw how Sierra's vector backgrounds work, they're really weird, but they also account for like the dithering and everything. It's interesting and at the same time very confusing, because some of those backgrounds, especially if you look at something like Space Quest 3, are like really complicated.
Space Quest 3, God.
Or
seen the backgrounds from that.
yeah, and stuff like what does have like too much dithering, like anything in like Conquest of a Longbow. Oh no, Conquest of the Camelot. That was pretty intense.
Yeah, it's quite interesting how they did that. As you said, with the divot fills, well, they didn't. There wasn't some artist locked up in a room just plotting each pixel individually.
Well, you would be actually surprised, because like the dithered fills are accounted for, but like if you look, I think there's a video actually on YouTube. It's called like The Art of Space Quest 3 or something like that. You can see how many dots Mark Crow actually put in by himself. Like those backgrounds are pretty insane.
Yeah, but with Sierra, they knew they had to do the dithering, so they put in a special dithering fill command.
If you run them in ScumVM, it does the basic pattern where you can merge the two colors together, but it looks weird if it's sandwiched in between two other ones, because those two stay the same. Yeah.
But with the vector backgrounds, they're just really awkward. I mean, they can be scaled up. The main advantage of them is that they can be scaled up to other video resolutions, but really, who would want to scale up like a background from a Sierra game?
Yeah, I always found that weird. I can understand in AGI days why it was done, why that would be saving memory and everything. But like when the backgrounds got really complicated in the SCI 0, I don't know. Like it's kind of weird how it drew them too, because it pre-drew them in the buffer and then it copied them, because you could have all kinds of transitional effects.
Yeah, they pre-drew them in like this buffer and some special segment of memory or something. I think it was like that video RAM.
Yeah, so then it copied everything, and then later on it just before you change the background, it just redrew the parts that moved where the views were. So I'm not sure how effective it was in anything, but I mean, I guess it worked. I mean, the art is gorgeous, not gonna lie, but it just seems to me like an additional pain in the ass for both artists and the system running it. But what do I know?
But with the early AGI games, they didn't have the buffer, so every time you move to a new screen, you'd just be like, "Oh wow, what the hell has happened?" Because it's drawing in the background. But basically, the early AGI games, they didn't have enough memory to do buffers, so they had to draw directly to video memory. That would make flickering, and most importantly, you could see them drawing the background, especially if you're running like an old IBM 5150. But that really spoiled some of the games as well. I mean, in King's Quest 1, you know the puzzle where you have to push over the rock to get to that area?
Yeah, the rock would not appear until the background is drawn.
Yep, so people are like, there's a secret area there. Thanks, slow processor.
Listen, any hints for the earliest Sierra games were welcome.
Yes.
And
those are cryptic on their own right.
I mean, that only applies to like the earliest Sierra games. I mean, look, by the end of by the
By
end.
Reaching Larry 7, they actually
Well, no, no, no. I'm
got
not.
around to making them user-friendly.
Yeah, but I'm not even saying that. But like, later AGI games fix that. I mean, look at the backgrounds in something like Manhunter, which I have a video of that on YouTube. Whoever's listening, and if you haven't seen the video, look up The Art of Manhunter on YouTube. Those backgrounds are probably, well, not probably, the most complicated backgrounds in AGI games ever, and they're pretty intense. And if you had to sit through all of them being drawn on screen, you'd be there forever.
Yeah, but by then, more advanced hardware came along,
Oh,
like
of course, yes.
286s, 386s, so the drawing was like flung over you, unless you were still playing on an Apple II, in which case you're like, how much longer is this 1 hour? Oh, I can wait that.
Yeah.
If you had like a tile-based game, well, if you had a game that used a lot of repetitive patterns, you might as well just store the patterns and then just fill them in the background so that RAM would be saved. I mean, I've also seen this thing where you used like little tiles to make up a room. I've seen it in old Commodore 64 games like Maniac Mansion where they used text mode.
Right.
They used their own text font. The lower 128 characters were the normal text font. The upper 128 characters were the room graphic tiles. So basically, the way they did that was the artist would draw the room, and then they'd press a key on the Commodore, because I've only seen this in Maniac Mansion. They would press the key or run it through some program which crunched it down into tiles. They would look for errors, correct them, and then put it through the crunching program again. And then eventually you got like a perfect room made up of tiles.
Mm-hmm.
There were other systems where this was the only way to make big room graphics, like the NES and the Game Boy, where they didn't have enough space for a bitmap buffer, so they stored everything in tiles.
Well, something akin to that we touch on in my podcast with Jim Leonard is the early CGA games that, CGA actually allowed for 16-color text mode. So very, very few games actually modified the character set and use CGA 16-color text mode to draw graphics. More so now. There's, DOS enthusiasts today who do that now, just as an exploit. But back, nearly 30 years ago, just like a handful of programmers actually achieved that.
Yeah. I've seen what you're talking about, the CGA text mode 16 colors, with this game called Paku Paku.
Paku, that was the big one from a few years ago. Because it's also a really good Pac-Man clone, like very functional. I think the older games are like something, Seven Spirits of Ra is one, and I always forget what the other one is by the same developer. Pretty impressive. Not so much unusual now that we know about it, but back in the day probably took a little bit of figuring out to do.
Yeah.
Actually, we're arriving at a very interesting point. So PCs weren't really designed for games. When games were made for early PCs, or not so early PCs really, there's always this balance of, yes, maybe IBM PC had more memory starting out than other platforms at the time, but they didn't have hardware sprites. They didn't have any hardware that was designed specifically for gaming, unless you count like sound cards that came later. So despite being able to work with a larger amount of memory, let's say, you always had to trade back for, everything had to be going through your CPU directly. So you always fighting for speed.
Yeah.
In the early days of DOS, and for a long time, really.
Yeah, you brought up a very interesting point there about the CPU having to control everything. That was a real downside of the PC, and the Commodore. It had a specialized graphics chip, a specialized sound chip that could take care of the heavy work.
Mm-hmm.
PC only had a little crappy Intel 8088. It running at 4.77 megahertz, and that's in theory, because actually it takes, I think it was twice as long to access code from the lower 128K of memory, so that effectively halves the speed to like 2 megahertz. Audio compression, soundtracks for games are usually stored in MIDI. That stores the events for the notes. Basically, think of it like as this. Think of it like this. Wave. Now, wave is like a recording of the orchestra. Tracker files is like the sheet music for it, and then a special instrument to play it for it with. And MIDI is just the sheet music. So the machine has got to use its own instruments in the PC, in the IBM PC's case, PC speaker, or if you were lucky, an ad-lib card. And MIDI music actually stayed around for quite a long time. And in fact, it's still being passed around today, so it had quite a large impact on us. Digital samples, you can't really compress those. I mean, I haven't seen ways you can compress those because it's kind of the unpredictability of the noise you're recording. I mean, so the only way you can really compress those is either lower the bit depth, I think it was. You can lower the bit depth to 4 bits, which means you can only have like 8 volume levels. Oh, wait. I think that's, yeah. So you can lower it to 4 bits where you can only have 16 individual positions the waveform can be in, or you can lower the sample rate. Now, most of the time, I'd recommend just lowering the bit depth because most of the time you don't need exact volume control, but most of the time the higher sample rate will sound better. Like, I'll give you an example.
Mm-hmm.
I've learned this from Jim Leonard on his talk about the 8088 corruption. It's better to use a higher frequency than a higher bit depth because I'll use one of his examples. Basically, you've got 2 audio files. One is a 16-bit 1 kilohertz sample of somebody talking, and the other is a 16 kilohertz 1-bit sample of somebody talking. It's the same person. They take up the same amount of space on the disk. But the 16-bit version, even though it's got that increased bit depth, because of the sample rate, it sounds like you're bludgeoning a whale underwater. And the 1-bit 16 kilohertz version, it will be quite crackly, but it is a lot more recognizable than bludgeoning a whale underwater. So, there's that. There are a few games that compress the audio samples, but that's with something like ADPCM, and again, that's got a patent on it by some greedy bastard corporation.
As with everything.
So, data compression was really important. And the other important thing was to get the game to run fast. Now, most people had a really slow computer. So you had to target those people with really slow computers. And basically, you had to use back-ass optimization. Basically, cheat your way through the program, trying to save as many bytes or as many cycles as you can, because you can't save both at the same time. You either save as many cycles as you can, or as many bytes as you can. I've learned this the hard way. The reason you can't is because for speed you usually need unrolled loops, and that takes loads of memory, because, you know, the unrolled loops thing. But if you use rolled loops, that saves loads of bytes, but it wastes loads of cycles. There's no real way to win the game. But there are some things you can do to speed it up. So the first thing you can do is shift the bytes when you're doing multiplication. Now, the reason you do this is the Intel 8088 or 286, basically every Intel processor has got a dedicated multiply instruction, and it is cripplingly slow. So on old games, well, if you wanted to do multiplication, you'd usually shift it, and you'd have to split it into powers of 2 to do the shifting, because remember, binary's based on either on or off, so it works on powers of 2. Like, if you shift it by 1 left, it multiplies by 2. If you shift it right, it divides by 2. So there are some quick ways to do multiplication and division. So, for shifting for multiplication, the only real way to get optimum performance out of shifting for multiplication is to have dedicated routines for each kind of multiplication. Usually, you won't need to have usually you won't need to use a generic multiplication routine. Usually, the only time you need to use multiplication is to work out the player's score or to calculate an offset to video memory. So, let's say you wanted to go to like x coordinate 160 and y coordinate, I don't know, y coordinate 319. I'm just picking numbers out of the air here.
Mm-hmm.
So what you would do is you'd take 319 and 320. It's not a power of 2, but you can split it into powers of 2. And the two powers of 2 that you can split it into are 64 and 256. So you take the number, you shifted 8 bits, and then in another register, you've got the same number, and then you shift that only 6 bits, which is the power to 64. So, and then you add the two numbers together, and that is your y coordinates for the video memory. And then to get to the x position, you just add on the x coordinate. Obviously, if you were using EGA, you'd have to halve it for whatever pixel you're addressing, because that only uses half a byte for each pixel. And for division, you'd obviously want to use dedicated routines for that as well, for each kind of division. So for division, you shift it to the right by 2. And before you shift it each time, you check the low bit to see whether it is on or off. If it's on, that means it's going to be a decimal number, which links in nicely to how to optimize decimal numbers. Basically, you use a 16-bit pair, one for a fraction and one for the actual whole number. It's a bit hard to explain. Basically, on the game I'm coding for the Spectrum right now, I use 16-bit pairs like that, like decimal numbers. Basically, I have a delta x value and a delta y value, so I add the delta x to the low byte, and if it's a carry, well, I increment the high byte, and since it's changed, I redraw the object. And you could do the same thing on IBM PC, if you had some game that uses inertia. Basically, you could use decimal numbers like that as fractions with the denominator being 256. It is complicated, and it is very hard to get your head round, but once you figure it out, it is actually a smooth ride. And a few other optimizations you can take are using the stack to swap around registers, and basically what you do here is, let's say to swap around these two registers, well, on the Intel 8088 there's no dedicated instruction for it. I know on the Z80 there is, but on the Intel 8088 there's no dedicated instruction to do those. So you push them, both of the registers you want to swap, onto the stack, and then you pop them back out, but in a different order. So let's say you push AX and push BX, but then you restore it as pop AX and pop BX. AX will now contain what BX used to contain, and vice versa. So that's the way to swap around registers on the 8088. Obviously, the Z80 had its own dedicated instruction that was a lot faster, but we're not working with the Z80. And sometimes there are a few times where you need to load a register. You need to load the accumulator with 0, or you need to check if the accumulator is 0. Usually what you'd do is you'd load 0 into the accumulator, but the quick way to do it is do an exclusive OR command against itself. Now, an exclusive OR, basically, it takes two numbers. It takes two binary bytes, and if the first bit, bit in the first byte or the bit in the second byte is on, it'll write 1 to that. But if both bits are off or if both bits are on, it will not. It will write 0. So if you do an exclusive OR command against the accumulator, since the command's set to do it against the accumulator automatically, that means it'll be the same binary byte. So it'll be either basically it'll reset itself because the ones that are there are repeated in the next byte, which is actually the same register, so it'll reset itself in essence. And that usually saves a lot of memory because you don't have to specify 0, and will save a few cycles because it's not loading that memory location into the accumulator. And the way to check if an accumulator is 0, well, the way to check if the accumulator is 0, you OR it against itself, and then you check, and then you jump depending on whether the 0 flag is set. Basically, if you wanted to jump back to return from this subroutine, if you wanted to jump back to another routine once A reaches 0, once the accumulator reaches 0, sorry, well, every time you would OR it against itself and then jump back if the 0 flag is set. This is a lot quicker than using the compare command because it just is. I don't know why it is quicker. It just is.
I see. See, all of my I did program a few games for DOS, but I always used just a lot of ready-to-go libraries, and I never got around to doing any assembly, or so I never worked with memory directly, which is a shame. I really should have, but I'm a lazy person.
What games did you code?
I did a few like adventure games. I did a few like action games. It's mostly when I was learning different programming languages. I would try to do games to the best of my extent using those languages. You know, everybody sort of started with QBasic and just rolled from there.
Yeah.
But you know, you could do a bunch of stuff in QBasic if you really wanted to, and if you used like a little bit of assembly, because like originally you couldn't use the mouse in QBasic, but I mean you could, because it allowed you could just execute an assembly command, right? So
Yeah.
I had this book. I did buy a book on game programming. I think the only book on game programming assembler in Russia, and it was a really shitty book that. It wasn't structured well. It was overly complicated, and just didn't. It didn't really. Somebody who wanted to write this book didn't really know how to write a book, I should say. And like, it had two.
So they were like me, basically.
And it had like two sort of appendixes, and one of them was literally a listing of Tetris, just a printout of a program, which was like half the book in assembler. Yes, that was the weirdest choice. There was no other. There was no other like no examples, no other examples in the book, right? Except for that, just a flat out printout of your basic Tetris clone in assembler, huge. But what another appendix that it had an appendix of sort of the most useful. It would give you interrupts and the parameters. For a lot of stuff, so you could, and I of course forget what they were now, but with a bit of a basic, just direct addressing in QBasic, you could easily enable the mouse and read the parameters because they were always the same, you know, the coordinates and the clicks. It was like some of the most basic stuff, and I mean, it was very common for programmers back in the day, even when, you know, not everybody's going to write their games in assembly, right? I mean, in the early days, that's what you had to do to achieve like maximum speed, right? So it was very impressive to see some really early like mid-80s 3D stuff, and you know, all of that stuff was just coded just like an assembler directory to be as fast and efficient as possible. But even as higher sort of languages rolled around, you know, people started programming in C, let's say, like, and you would still look at the source code for like old games that are available, and a lot of the routines are just a flat assembler code, just for speed, because it would still be more efficient to do it that way and just let it roll, versus coding routines in C, and which wouldn't not be efficient, and fast enough for games especially.
But what you said about the 3D stuff, there were a few early 3D games like id Software's Wolfenstein 3D.
Well, I'm talking even before that, in the 80s, I mean, Wolfenstein 3D is like Borland C code, but you can see like huge chunks of it are assembler.
Yeah, but I was quite surprised when I saw quite a bit of it was written in C. I was like, they can't do that if they're planning to run this on a 286.
Yeah, but then you've seen how much assembler is in there, right? So and on a 286, I mean, Wolfenstein didn't really run that well on a 286. I played the Wolfenstein 3D on a 286, and it's not that
great. You could run it if you set your window size to like a mouse size. You could run it if you set your window size to 1 pixel by 1 pixel. That's how it
works. It's you didn't have to make it the smallest possible to play pleasantly, but like about half, I'd say about half would give you some decent speed depending on how complicated things got. But still, I mean, talk something about like really early 3D, like any of the 80s flight sims, or Indy 500 would be the best example that everybody knows is like game that looks super good and runs on the original hardware like at a decent speed, just because it's all just flat assembler code with lots of optimizations.
There's a lot of talk these days about offloading quite a bit of the work to the GPU.
Mm-hmm.
And I find that quite funny, because in the 80s, the GPU didn't even exist. At most, you had on the Amiga, like the Blitter, which copied data from location to location. In the video RAM, that was it. Nowadays, they're talking about offloading everything, and they're complaining their graphics cards aren't, fast enough to handle these graphics. And I'm like, why don't you do a bit of flat assembler code to do some on the CPU? In those extra cycles you've got.
Yeah, it's funny, isn't it?
Yep. I think the art of assembler has really been lost in these new languages.
Oh, of course. Just generally, like I was, I'm a shitty programmer, but as soon as I got my first Android phone, I was like, hey, look, I can do stuff for it, right? So like I just literally ported one of my lazy prototypes on my Android phone, and it ran flawlessly, full speed. I didn't do any optimization for mobile or anything, and I was like, oh my god, nowadays you can really be lazy and just take advantage of those like super fast devices that we have. So there is probably very little need to do as much optimization as you can. And then you look at on Twitter, and occasionally John Carmack posts something very ridiculous, and you're like, well, there's at least a few people left in the world.
Truly, the only way you could optimize your routines to draw stuff to the screen, the only way you could really optimize anything is only updating a slight part of the screen every frame, only a slight part of it. Now, in adventure games, you're only updating a slight part of the screen, so you've got that problem out of the way. Because, in adventure games and the whole explore, you only have the character moving. But anyways, don't want to derail again. Anyways, so the thing is, you can't copy an entire 16K screen buffer every frame. And if you could, you'd probably only have like 10 cycles left for actual math operations.
Mm-hmm.
So what you need to do is only update a part of the screen. And you might say, well, that might cause flickering because we don't know where the scan line is at any one time. To that I say, every time your main loop of code is over, wait until the next frame is issued. I think you can check the VGA. I think you can check the CRT controller for that on some older systems. But that's what I say. Just check the CRT controller. If it's in the vertical blanking period, then copy your sprites. Because honestly, if you copy them halfway down the image, it's going to look like absolute crap. It's going to be flickering all over the place, and in some cases, some people's heads may be split into two. Very painful decapitation, might I add. Do not try it at home. So only update sprites during the vertical blanking period, and if it's past the vertical blanking period, only update sprites that are at the absolute bottom of the screen. Because even then, it's still risky. Because on old systems, the scan line just flies by. The processor can't keep up. So you must update them you must update them kind of like priority based. Basically, you don't update all the sprites, you only update one of them. Because, I mean, with newer systems, you can get away with updating the whole screen every frame. On older systems, you can only update a tiny section of the display every frame. That is, unless you're erasing the screen, in which case you're probably using a rep move string command, in which case, yeah, you'll reach the end of the screen before the scan line does. It's a complicated business, basically. My advice would be just update sprites in the vertical blanking period. That wasn't really optimization, but anyways, it fits under the topic of making it look better and faster and smoother. That's all the optimization tricks I've got.
You see, this was absolutely necessary in DOS because, well, old computers didn't have the same amount of storage or speed that we have today. There was one notable example of a programmer called John Connolly who did basically the absolute best optimizations in the field. He used mostly assembler for his games. His claim to fame was Wolfenstein 3D and Doom, which were absolutely amazing when you consider it was 1992 when Wolfenstein 3D came out. I mean, it was full 3D shifting. It was a full 3D environment with gods and music, and it was amazing on the PC.
And this is it for this episode of the podcast. I hope you enjoyed listening to it. And I would encourage everyone to, who is even a slight bit interested, to try out programming for DOS. Now, as I've mentioned before, you don't really have to learn assembler to do anything, but it's cool to sort of experiment with programming on a lower level. So you can always sort of find out how to do assembler code, like little tidbits of code inside like a higher end language, and try it out. And nowadays with DOSBox and everything, you're not gonna ruin anything. You're not gonna fry your machine. So I would encourage you to sort of look up some maybe graphics or timer or sound commands, and you'll see how it is. Start with the mouse thing. Mouse is the easiest. Put a mouse pointer in your QBasic programs. Experiment. Well, so this is it, and you can follow me on Twitter at DOSNostalgic. And thanks, John, for being here. Goodbye.
I must say it's been a pleasure to be on here, and goodbye.